Hello everyone. So I'm going to show you in this video how to convert an Epsilon-NFA into its NFA representation. In other words, given an Epsilon-NFA machine, our objective is to remove all Epsilon transitions from that machine. And as you all know, I have uploaded for you in a previous video how to convert a NFA machine into its DFA representation. In that case, for a given computing problem, you can design its non-deterministic machine, and by applying those algorithms, you can convert your non-deterministic machine into a deterministic machine. And as you know, it's always easier to implement a deterministic machine to check whether a given string is accepted or rejected by your machine. So to summarize, for any computing problem, you can design the non-deterministic machine, then you apply those conversion algorithms to convert your non-deterministic machine into a deterministic machine. And this is the objective of those conversion algorithms. Now, moving on to the algorithm that will allow me to convert my Epsilon-NFA into its NFA representation. So the algorithm is very simple. It consists of 3 steps. Step 1, for each state, we have to check where that state goes on E closure. So I'm going to define in 5 minutes in this video how to calculate the closure of a given state. Then in step 2, the obtained set of states by applying step 1 have to be checked to which states they go for a particular input over my alphabet. Then in step 3, the obtained set of states by applying step 2 have to be checked again to which state they goes on E closure. So by applying the closure property, in that case, all epsilon transitions will get removed from your machine. And this is our objective of converting an Epsilon-NFA into its NFA representation. So I'm going to solve in this video several examples to show you how to apply that algorithm to convert our Epsilon-NFA into its NFA representations. So here I put for you several notes. I will go back to them in few. So let me start with this algorithm, with this example. So here, this is a machine that consists of 3 states. We have state A, B, and C. My starting state is A. My final state is C. And as we can see here in this machine, I have 2 epsilon transitions. I have one epsilon transition from A to B and another epsilon transition from B to C. So now I'm going to apply the steps I have in that algorithm to convert that Epsilon-NFA machine into its NFA representation. So this is my machine. As I said before, I have 3 states, A, B, and C. A, this is my starting state is A. This is my final state, which is C. And 2 epsilon transition, A to B, and another epsilon transition, B to C. Now, let me go back to my steps in that algorithm. Step 1, for each state, it means for state A, B, and C, we have to check where they goes on closure. To do so, I will start with the state A, followed by B, followed by C. Let me start with the state A. So this is A. So now I will show you how to check, how to remove epsilon transitions from state A. So let me take that symbol of closure. So this is a closure. I will do for all inputs, for all symbols over my alphabet, which in that example are 0 and 1. Again, I will put the closure symbol. So again, let me read step 1. Step 1, for each state, check where it goes on E closure. So I will start with the state A, followed by B, followed by C. Now, moving on to the definition of E closure. It's here in note 4. E closure, how to calculate the E closure of a given state. The E closure, by definition of the state Q, denoted by E close Q, which is sigma star, is a set that contain Q together with all states that can be reached starting at Q by following only epsilon transition. So in that case, the closure of the state A is the state A and any state that can be reached by epsilon transition starting from A. So if I go to A, to that machine, can I reach B starting from A by seeing epsilon? Yes. Therefore, the closure of the state A is A, B. Now, can I reach the state C starting from A by seeing only epsilon transition? The answer is yes. Why? Because I can go A to B by epsilon transition, and I can go from B to C by seeing an epsilon transition. Therefore, the closure of the state A is 3 states, A, B, and C. Now, let's apply now step 2. The obtained set of states by applying step 1 have to be checked to which state they go for a particular input. And here my input is 0. Now, A given 0, according to this machine, it's A. Now, B given 0, it's the dead configuration phi. Let me add that symbol. So here I will put phi. I don't have a target destination at state B given the symbol 0. Now for C given 0, I have a self loop which remains C. Now I will go to step 3. The obtained set of states by applying step 2 have to be checked to which states they go on E closure. So same, I will do the closure of A, the closure of phi, and the closure of C. So as you can see here, let me repeat again the definition of the closure. The closure of a given state, Q for example, is the set of states that contain Q together with all states that can be reached starting at Q by following only epsilon transition. So again, it's A. Then, can I put B? The answer is yes. Why? Because starting from A, I can reach B by seeing epsilon transition. So it's B. Now, what about C? Should I put the state C? Yes or no? The answer will be yes. Why? Because I can reach C from A by seeing only epsilon transition. In other words, I can go from A to B using epsilon, and I can go as well from B to C by seeing epsilon. Therefore, the closure of the state A is the states A, B, and C. Now, what about the closure of phi? It's nothing. So by definition, the closure of the dead configuration is nothing. What is the closure of C? So first of all, it's the state itself, which is C, and any state that goes from C by seeing only epsilon transition. As you can see here, I don't have any epsilon transition that start at C and goes to other states. Therefore, the closure of the state C is C only. So now I finished my job for the state A for the input symbol 0. Now I have to continue the process. I have to do the same job for the input alphabet 1. So again, I will put the state A. Okay. Same process. But now I'm going to apply it for the input symbol 1. Again, what is the closure of A? It's A, B, C. A, B, and C. Again, the A given 1, I don't have any destination, so it's the dead configuration 5. Okay. B given 1, I have a self loop, so it's B. Now C given 1, again I have a self loop on 1, it's C. So now I will do the closure of that configuration phi, followed by the closure of B, followed by the closure of the state C. Now the closure of that configuration is nothing by definition. Now the closure of the state B, by definition, it's B, and any state that can be reached from B by seeing only epsilon transition. So the closure of B, it's B. Now what about C? So yes, I can add C. Why? Because simply starting from B, I can go to the state C by seeing epsilon transition. So the closure of B, it's B and C. Now I will do the same. What is the closure of C? It's the state itself, C, and any state I can reach starting from C by seeing epsilon transition. As you can see here, I don't have any transition to other state. Therefore, the closure of the state C is only C. So now I finished my job for the state A. I'm going to apply the same process for the state B and for the state C. As simple as that. This is the algorithm. Very simple algorithm. It uses the closure property to remove all epsilon transitions from your machine, and in that case, your machine will become NFA. Now I'm going to apply the same process for the state B. So this is B. So I will do closure. So I will do for, let me do a copy paste. So I will do for the input symbol 0, then for the input symbol 1, and here I will put the symbol closure, 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 closure. Okay, that's it. So now closure of B, as it was mentioned before, the closure of B, it's two state, B and C. C. Now B given 0, it's 5. I don't have any target destination at B by seeing 0. So I will put the symbol 5. Okay, now C given 0, it's a self loop, it's the same state, C. Now I will check where phi goes on E closure, where C goes on E closure. As we all know, by definition, the closure of that configuration is nothing, and the closure of the state C is the state C itself only. So now I finished my job. I removed all epsilon transitions at the state B for input alphabet 0. Now I'm going to do the same process for the input symbol 1. So now the closure of B, so it's B and C. Now B given 1, here I have a self loop, it's B. Now C given 1, it's a self loop, it's C. So now I will calculate the closure at B and C. So as we all know, the closure of B is B comma C, and the closure of C is only C. So now I finished my job for the state A and B. I will do the same now for the state C. Same process. So this is for my state C. I will do the closure for input alphabet 0 and for input alphabet 1. So let me do a copy paste back. So here I will do it for the input symbol 0 and for the input symbol 1. Okay. Let me take the symbol of closure. This is closure, this is closure. Okay. So the closure of C is C. C given 0, it's the state itself, it's C. And the closure of C, it's C. Now closure of C, it's C. Now C given 1, it's a self loop, it's C. And the closure of C, it's C. That's it. So now I have applied the 3 steps of converting our Epsilon-NFA into its NFA representation for all the state. So now I'm going to draw my NFA machine. So now I will go back to my notes. So in note 1, initial state remains the same, which means my initial state in my Epsilon-NFA representation, which is A, remains the same in my NFA representation. So here my starting state will remain the same. So let me put A. This is my starting state. Okay, that's it. Second note, no change in the total number of states, which means in my Epsilon-NFA representation, I have 3 states, A, B, and C. And then when I convert my Epsilon-NFA into its NFA representation, the states will remain the same. If I have 3 states in Epsilon-NFA, it will remain 3 states in my NFA representation. If I have 5 states in my Epsilon-NFA, it will remain the same in my NFA representation, and so on and so on and so on. So here no change in the total number of states. So here I have ABC. I will have always in my NFA representation A, B, and C. So no change in the states. So I will put A, B, and C. Now I will put the transitions by seeing those tables. Now A given 0, you do the merge of all those states. A union B union C union C, it's A, B, and C, which means A given 0, it has a self loop on A, and it goes to the state B, and it goes to the state C. This is by seeing the input alphabet 0. Okay, that's it. Now what about B? Or let me finish with A. A given 1, according to that table, A given 1, you do the union between B, C, and C. It's B, C. So A given 1, it goes to B and C. So I will add here, comma, 1. Let me add my 1 here as well, comma 1. Which means at the state A given 0, I have a self loop, and A given 0, it goes to B, and A given 0, it goes to C. Now A given 1, it goes to B and C. And as you can see here, my machine is non-deterministic. Again, as I said before, my objective is to remove only epsilon transitions. So as we can see here now at state A, I don't have anymore any epsilon transition. Okay, now I finished my job for the state A. Now I will continue with the state B. Now B given 0, you do the union of nothing and C, it's C, which means B given 0, it goes to the state C. Now, according to that table, B given 1, you do the union of B, C, and C, it's B, C. So here for at the state B, given 1, I have a self loop, given 1, and I have, it goes to C. So let me add the symbol 1 here. Okay. So now for the state B, given 0, it goes to the state C. Given 1, it goes to the state B and C. So now I finished my job for the state B. Moving on to the state C. As you can see here, I will have C given 0, it goes to C. C given 1, it goes to C. So here it means I have a self loop for my input alphabet 0 and 1. Okay. So now I finished the transition of states. Now moving on to the last step to do to finalize my machine, which is presented in note 3. As for the set of final states, it can, so first of all, if I have a final state in my Epsilon-NFA, it will remain the same in my NFA representation. So here it means I have C as a final state, therefore C will remain a final state in my NFA representation. Okay, this is the first step. Step 2, let me read that very nice note. As for the set of final state, it can contain any state that can reach any of the final state by seeing only epsilon, which means the question here, is A final? This is the question. So if I can reach from A final state by seeing epsilon transition, then A will be final. So let me check. Can I reach from A final state by seeing epsilon transition? The answer is yes. Let me show you. Here, from A to B, I can go with epsilon transition, and from B to C, I can go with an epsilon transition, and here C is final. Therefore, yes, starting from A, I can reach a final state by seeing only epsilon transition. Therefore, the state A is final. Now, what about the state B? Is it final? Again, I will check. Can I reach from the state B a final state by seeing only epsilon transitions? Let me check. The answer is yes. Why? Because at B, I can reach the final state C by seeing an epsilon transition. Therefore, the state B is final. So I will put here a double circle to represent that the state B is final as well. So as you can see here, as a conclusion, this is my NFA machine by applying that algorithm. As we can see here, it's a non-deterministic machine. Furthermore, and the most important is, we don't have any epsilon transition. All epsilon transitions were removed by applying the closure property in the following tables. Okay, so to summarize, this was my Epsilon NFA machine. By applying that algorithm, the NFA machine will not contain anymore any epsilon transition. Definitely, I'm going to upload that PDF file along with the video. Now, moving on to another example. Same example, given that epsilon NFA, I'm going to convert that NFA, that epsilon NFA, into its NFA representation. Okay, so I will put that epsilon NFA here. So as we can see here in this example, it's an epsilon NFA that consists of 4 states: state A, B, C, and D. The starting state in this example is A, and the final state is D. And as you can see here, I have one epsilon transition between B and C. Here it means I can go from state B to state C by seeing an epsilon transition. So now again, I'm going to apply the steps I have in that conversion algorithm to convert my epsilon NFA into its NFA representation. So here I will do the process for 4 states, A, B, C, and D. Let me start with the state A. So I will, here my input alphabet are 0 and 1. So I will apply the process for input alphabet 0 and input alphabet 1. So this is a closure, 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 closure. Now, what is the closure of A? It's the state A and any state that can be reached from A by seeing only epsilon transition, as we can see here. So first of all, it's A. Do I have another state in the closure? The answer is no. Why? Because I cannot reach from A any other state by seeing only epsilon transition. Therefore, the closure of A is A. Now, A given 0, it goes to B. Now, what is the closure of B? So it's B, the state itself, and any state that can be reached from B or starting from B by seeing only epsilon transition. Here, is C part of the closure? The answer is yes. Why? Because I can reach C from the state B by seeing an epsilon transition. So the closure of B, it's B and C. What about D? The answer is no. Why? Because I cannot reach the state D starting from B by seeing only epsilon transition. بتخيل مفترض تكون الرؤية صارت واضحة. That's it. This is all about the closure. Okay. So now moving on to the input alphabet 1. The closure of A is the state A only. Now A given 1, as we can see here from that epsilon NFA machine, if I am at the state A, I don't have any target destination for the input symbol 1. Therefore, A, by seeing 1, I will put the dead configuration. I don't have a destination. Then, what is the closure of the dead configuration? It's nothing. Okay. Now I will do the same for the state B, C, and D. Let me do the same process for B. So I will do for input alphabet 0 and for input alphabet 1, I will do the double closure to remove all epsilon transition from my Epsilon-NFA machine. Now the closure of B, as I calculated before, it's two states, B and C. So it's B and C. Now, according to my Epsilon-NFA machine, B given 0, it goes nowhere. I don't have a destination at the state B given the symbol 0. So here I will put the symbol phi. Now, what is C given 0? It's a self loop, same state. It will be C. Now, what is the closure of phi? It's nothing by definition. What is the closure of the state C? It's the state itself, C, and any state that can be reached from C by seeing only epsilon transition. As we can see here from that Epsilon-NFA machine at C, I cannot reach any state by seeing only epsilon transition. Therefore, the closure of the state C is only C. So now I'm going to do the same for the input symbol 1. So again, what is the closure of B? It's B and C. Now B given 1, according to my machine, B given 1, it's a self loop, it's the state B. Now C given 1, it's the state D. Now the closure of B, it's B and C. The closure of D, it's the state itself and any state that can be reached from D by seeing only epsilon transition. As we can see here from that Epsilon-NFA machine, I cannot reach any state from D by seeing epsilon transition. Therefore, the closure of the state D is only D. So now I will do the same for the state C. So this is C. So now closure. So I will do the same process for the state C for the input alphabet 0 and for the input alphabet 1. Closure, closure. Closure and another closure. Okay. So what is the closure of C? As it was mentioned before, it's the state C only. Now C given 0, it's C. Closure of C, it's C. Now closure of C, it's C. And C given 1, it's the state D. And the closure of D, it's only D. That's it. Okay, so now I'm going to finalize that process for the state D. So I finished my job for the state A, for the state B, for the state C. One more state is left, which is the state D. Again, so I will check where it goes for the input symbol 0 and input symbol 1. Same process. So this is 0. This is 1. Let me take the symbol closure tag. That's it. So same process we apply to all states we have in our Epsilon-NFA machine. Now what is the closure of D? It's D. Now D given 0, as you can see here, I don't have any destination at D for 0 and 1. Therefore, D for input symbol 0, it's the beautiful symbol phi. Very beautiful symbol. What is the closure of phi? Nothing. Now D. Let me put that line above D. Okay, no problem. Now, closure of D, it's D. Now, D given 1, it's phi. And the closure of phi is nothing. That's it. Okay. Now, I'm done with my tables that will tell me what are the transition from one state to another state given the input alphabet 0 and 1s. Now let me start drawing my machine. I will go back to my beautiful notes. The first note is initial state remains the same, which means the initial state here is A. So in my NFA representation, that state will remain the same. So here it will be A. And this is my starting state of my NFA representation. Second note, no change in the number of states, which mean, in other words, the states will remain the same. There is no difference. So here I have states A, B, and C. I will have in my NFA representation also the states A, B, C, and D. No change in the states. So let me add those states. Let me suppose this is my state B, and this is my state C, and this is my state, for example, D. So here I will put B, for example, and here I will put the state C, and here I will put my state D. Now, upon those tables, I will know my transition. A given 0, it will go to which state. A given 1, it will go to which state, and so on, and so on, and so on. So let me start with the two tables for the state A. Now, A given 0, it goes to two states, B and C. B and C. So let me put here 0, 0. Okay. Now, A given 1, it goes nowhere, which means at the state A, given the symbol 1, I don't have a target destination. وما في أي مشكلة. Why? Because it's non-deterministic. Definitely. So far, I finished my job for the state A. Now I will work for the state B. Now, as we can see here from that table, B given 0, it goes to C. That's it. So this is for the input 0. Now, B given 1, according to that table, it goes to three states, which are B, C, and D. So first of all, for 1, I have a self loop. This is for 1. It goes to C. So I'm going to add here, comma, 1. Okay. And it goes to the state D. So let me, that's it. This is by seeing 1. So now I finished my job for the state B. B given 0, it will go to the state C. B given 1, I have a self loop on B. It goes to C and it goes to D. Now what about the state C? I will check that table. C given 0, I have a self loop. So let me put here a beautiful self loop for the input symbol 0. Now, according to that table, C given 1, it will go to the state D. That's it. So here, by seeing the value, the input symbol 1. Okay. Now, what about D? As we can see here, D given 0, it goes nowhere. D given 1, it goes nowhere, which means at the state D, given 0 or 1, I don't have a target destination. Now, one more thing is left to finalize that NFA is to check what are the final states in that NFA representation. So first of all, in my epsilon NFA, D is final, therefore D will remain final in my NFA representation. That's why I will put here a double circle on the state D to indicate that the state D is final in that machine. Now, let's move and read again my note 3. As for the set of final state, it can contain any state that can reach any of the final state by seeing only epsilon. So let me check. Can I consider A final? Let me check. In other words, can I reach a final state from A by seeing only epsilon transition? As you can see here, unfortunately, I cannot reach a final state, which is D, by seeing only epsilon starting from A. Therefore, A is not a final state. Now, I will do the same for B. Can I reach from B a final state by seeing only epsilon transition? Again, I can reach C, but I cannot reach from B a final state by seeing only epsilon transition. Therefore, B is not a final state. Now, what about the state C? Now, the question will be, can I reach from C a final state by seeing only epsilon transition? Again, the answer is no. I cannot reach from C a final state by seeing only epsilon transition. Therefore, the state C is not final, and that will be my final NFA representation. In that machine, I have 4 states. Again, A, B, C, and D. My starting state remains the same, which is A. My final state here in this example is only one state, which is the state D. And here, clearly, we can see that that machine is non-deterministic without epsilon transition. And therefore, by applying that algorithm, we can see clearly I moved from an epsilon NFA machine into an NFA machine. Moving on to another example. So here I put for you at the end another example to practice. So this is an example, and this is the sample solution, and this is the resulted NFA machine. Thank you for watching. If you have any question, feel free to contact me via WhatsApp or by email, and see you soon.